Go away or disappear, right? Why is it, it's okay? Okay, now we are really going into totally a different topic, but of course related to climate change. If you recall, I did talk about carbon cycles that are actually being incorporated into the full modeling framework today. Now, that doesn't mean that carbon cycle models were not existing and our understanding of carbon cycle is suddenly improved or nothing like that. These models were, of course, being developed and our understanding was there prior to that. But now what I mean is they are basically we are putting them as a feedback into the whole Earth system modeling framework. That's all. So we did have carbon cycles as separate component even in the last decade or 2 decades back. Okay, now let us actually, I mean here again, this is a very preliminary lecture on the global carbon cycle. In fact, as we will see in this talk, you will hear about, you do hear about multiple, things happening in this Earth system, and they are all believed to change the environment in one way or other. Now, eventually, you need to put everything into the same framework. You can't compare apples and oranges. So you need to really, ultimately what you have to do is, you have to bring everything, every forcing agent and its influence on the climate system in the form of watts per meter squared. That's the way we have to do it. And when you do that, you will find that CO2 has the largest positive radiative forcing on the climate system right now. Okay, so that is the reason why carbon has become so important. Understanding carbon has become, particularly in the context of climate change, it has become very important. And so I will give a very brief overview about it. Now, okay, let's look at this. Why we are looking at this? CO2 is the main driver for the 20th and 21st century climate change. So we will quantitatively show that why CO2 is the dominant one. And then the projection of future climate change requires a good understanding on the controls of atmospheric CO2 concentration. What I mean by atmospheric CO2 controls of that. I think there is something else going on, that is, the carbon that we put into the atmosphere. I mean, it doesn't stay forever there. There are some processes. Fortunately, nature is doing a good job by removing the carbon dioxide that we put into the atmosphere. So, the question is, what are those processes and how fast they are operating? I think that is what we need to understand. Suppose these processes are really fast, let's assume, the removal processes, then we wouldn't be having this climate change problem. For example, the removal process, one good example for removal process is plants use CO2 from the air. Now, let us say there is a mechanism by which these plants are permanently, take the CO2, atmospheric CO2 and put it somewhere. Then, you don't have to worry about this problem. So, obviously, there are some controls by which the rate of CO2 that is taken up by plants or other physical processes, there is a rate at which it's happening. So, what are those controls? So, we need to understand. If you have a good understanding, maybe we can manipulate nature itself. People have in fact suggested many artificial ways to accelerate the natural processes by which we can actually remove atmospheric CO2 concentration. So, carbon is tightly linked to it because it is the dominant, warming agent right now. And if you understand how nature can be manipulated, first we need to understand nature. Then only we can talk about the manipulation of it. So here, of course, in this section we will talk about how nature is actually removing the atmospheric CO2 that we put into the atmosphere by fossil fuel burning. Okay. Next is there is going to be a change between land, atmosphere, and the ocean. So, how that is taking place. Now, this is a this is a figure from the latest IPCC report to illustrate the radiative forcing. Radiative forcing is basically, it tells you how much these agents are basically heating the planet, at what rate they are heating the planet compared to the pre-industrial time. So, if you look here, these numbers here, so the numbers are given here. So for carbon dioxide, it is 1.68 parts per meter square. Okay. Now, methane on the other hand, we have to look at the two colors here. But anyway, methane is about 0.5. There are methane induced field packs, which are this number. But if you look at the bars, the CO2 seems to have the length is largest for CO2, 1.68. And since pre-industrial time, this is the forcing for 2011, and this is 1980, and this is 1950. But anyway, now we have to be concerned about the most recent period. The most recent period, if you look at it, the radiative forcing, the combined radiative forcing is 2.29. So, and you can of course say aerosols have a negative radiative forcing because aerosols cool the planet by scattering, right? And then there are, of course, some other agents like land cover change. You can see that is negative. Solar, the uranium change, it does slightly warm the planet. But anyway, the major storage, you can see that CO2 is the dominant number, 1.68, while the total is only 2.22, right? So it's a major component of the current climate change. And also our understanding is listed here. Whenever you have a GtClyr, EH, that is very high understanding. So our understanding of the CO2 problem is very high. Okay. On the other hand, there are some problems like the effect of aerosol on the clouds. You can see that very low. Okay. And then here the land cover change is medium, and even aerosol actually is aerosol I'm surprised is high. But anyway, the point is that we have very high confidence of the impact of CO2 on the climate system, and that is the major driver. Okay, so yeah.
Is this level of confidence something related to the uncertainty of that bar?
Yeah, the uncertainty of that bar that is shown here. So you can see in the case of the clouds cases, this is the uncertainty, this length of the arrow such as that. So here this is the length of that. So that those numbers are also it's given in the bracket here. What is the range? What is the range it would be? Okay. So for CO2 that range is small. Okay.
Why landfill is a negative?
Huh?
Why landfill?
Landfill is negative because in the historical period, what has happened is most of the forests have been converted to croplands or grassland. Now, the croplands or grassland, they have higher albedo, so it's albedo effect. So they reflect more sunlight compared to forests. Forests absorb more solar radiation than grasslands. So it's a negative force. Okay. Okay. Now I think this is something. First, in global carbon, we deal with big numbers. So atmospheric CO2 is I'm sure you must have heard about parts per million. Really, what it means? What it means is, let's say in this case, ppm means parts per million. That is one molecule of CO2 for every 1 million air molecule. That is the exact definition. It has nothing to do with volume, so you can. This is the definition. In fact, in the afternoon there will be an assignment. Please remember the definition. 1 ppm means 1 CO2 molecule for every 1 million air molecule. Okay? Okay. Now, carbon stocks and fluxes are quoted in either gigaton or petagram of carbon. So that is petagram is 10 power 15 grams of carbon, or gigaton is basically 10 power 9 tons of, it's the same thing. Okay? So that's the unit for carbon. And in fact, there is you can do a conversion. 1 ppm. I mean, in the morning, I showed you what is the mass of the global atmosphere, right? So if you use that number, global, and this definition of ppm, you can actually use some simple algebra to show that 1 ppm for that atmosphere is equal to 2.1 petagram of carbon. So it's a huge amount of carbon. In fact, giga is for a billion, right? So 1 ppm means 2.1 billion tons of carbon. Okay? Now, of course, 1 mole of carbon is equivalent to 1 mole of CO2 because CO2 has only 1 molecule of 1 atom of C, right? And 12 gram of carbon, if you take 1 mole, that has 12 gram of carbon, which is also equivalent to 44 grams of CO2. Now, why I have actually put this figure? So you can actually show that if you convert 1 gigaton of carbon into CO2, this is a multiplying factor, 3.67. I think the reason I'm showing you is that if you read some papers, sometimes you will see that gigaton of CO2, sometimes other papers refer to gigaton of carbon. So you need to be aware that they differ by they refer to the same thing, but there is a factor of 3.67 involved in that. That is basically, that comes from 44 by 12. Yeah?
When you calculate the weight of carbon, this methane, carbon monoxide, everything is considered.
Yeah, that's a good question. In fact, it is there in the previous slide. I didn't want to really deliberately cover it. So you can see here, if you look at the CH4, that is the emitted compound, but these are the resulting compounds. So, so in fact, CO2 radiative forcing is a bit covered in this also. So you have to actually add, but it's a different story. You know, whether you consider concentration or emission, then it goes into that question. Let's not worry about that right now. Okay, so that's the unit for carbon. Now, yeah, tell me now, I just defined what is a ppm. So, anybody has an idea what is the latest number for this ppm? What is the current atmospheric CO2 concentration? Yeah, very close to 400 ppm. Very close, but not quite there. So, this is the number here. So, for the past 3 years, so you can see approximately it is increasing by about 2 ppm or so. Each year it is increasing. So, it used to be 389, 391, and I think in 2030 probably 395 or so, 95 point something. Now, you know, the actual instrumental measurement of CO2. You know, we didn't have this pre-industrial time. Actually, it started only in 1958, and there is a scientist who actually started this measurement. So he started this measurement in Manalova, which is a very remote area. He chose that location because you know, there could be local influences on the measurement. So to get a global, you know, to get a representation for global mean value. He chose the location, you know, somewhere around 3.500 above the sea level, and it's a very remote area. Now, you can see that since that time, I mean, I don't think we need any statistician to prove CO2 is increasing here. I mean, right? You can clearly see that, you know, it was at 310 ppm around 1958 when the measurement started. Today, we are touching 400 ppm. So, there is an, you know, increase of very close to 90 ppm, right? Or you can really convert that 90 ppm roughly by multiplied by 2, that is 180 billion tons of carbon load actually has increased in the atmospheric sea. Today, concentration compared to the time when it started, we have close to 180 gigaton of carbon sitting in the atmosphere. More CO2, more carbon sitting. Okay, I think, I have few questions. Okay, so, you know, this is a now very vigorous program. You know, a lot of people around the world are measuring CO2. And in fact, this is one of the highly monitored quantity right now. So in fact, you can see how, you know, compared to previous years, how December values are changing. So the December 2013 it was 396. Okay, so I think this is constantly updated. In fact, if you go to the web, you can even get daily values, daily values of CO2 measured every month. It's constantly being updated. This is one of the right now most closely watched atmospheric measurement. Okay, now that was in the last 5 decades or so. Now, what is happening in the last 5 years? You can see, this line shows the monthly data. And monthly data can be used to actually construct annual means. So you can see that steady trend here. Now, I think, okay, you can see approximately it is increasing by 2 to 3 ppm each year. And now, can somebody tell me why? You can see CO2 has an annual cycle. This is 2009 and this is 2010. And this is 2011. So it has a very nice sinusoidal cycle within the year. So if you look at it carefully, you will see that the CO2 concentration is actually high. Around winter and springtime actually is high. And then as you head into summer and the end of summer, it is actually the lowest value. Huh? Yeah, it is basically northern hemisphere plant. Now, if let us say plants are equally distributed in the southern hemisphere and northern hemisphere, will you see this?
Yes.
How many of you say yes? How many of you say no?
Yes.
How many of you say no? Nobody. What is the reason?
Most of the body is covered by ocean.
I don't know, he hasn't understood my question. I think my question is, if plants were equally distributed in the southern hemisphere and northern hemisphere, will you see this seasonal cycle? Why not?
That time it will equally distributed that carbon. In southern hemisphere also, that side will not see this.
Okay, anyway, the correct answer is, the reason right now we see this seasonal cycle is because most of the landmass is located in the northern hemisphere. And what's happening is, the photosynthesis, if you calculate on the planet, let's say photosynthetic activity, average over the entire planet, it will be skewed to the summer of the northern hemisphere. Because you can, for a good approximation, you can imagine the southern hemisphere has no plants. So, if you average the photosynthesis activity around the globe, it's going to be northern hemisphere summer. Now, if plants are equally distributed, then you're not going to be, the photosynthetic activity is going to be uniform, right? I mean, whenever we have winter, the southern hemisphere will have summer, and the photosynthetic activity in the southern hemisphere will be active. So you wouldn't see this seasonal cycle. So it's really because of the rigorous photosynthetic activity in the northern hemisphere that pulls the CO2 down during the winter and the spring. Right? Is that clear here? Yeah. Okay, now I think these are some of the lot of monitoring that is following, that is basically on the CO2 concentration. This was basically a news in Nature Neuroscience in last year August, when actually CO2 actually crossed 400 ppm on a daily basis. Okay, because if you see the month, this is May. So May is the time, basically springtime. The summer is really officially defined as June. Okay, so the springtime basically CO2 reaches the highest value, right? So you can see that it actually crossed for a week or so. It was about 400 ppm. But of course, then heading summer, what will happen is photosynthetic activity, June, July, August will pick up. The CO2 is going to go down. Okay. So the annual average 400 ppm, it may happen in another 2 or 3 years. It's not going to happen even this year, okay? This year or next year also. Yeah.
What increase the heat cover in southern hemisphere? The recovery increase Economic of CO2.
Okay, now I didn't really quite completely explain. What is happening is plants do both photosynthesis as well as respiration. Okay, now you can imagine the respiration is constant throughout the year. Right? I mean, of course, it does increase with the warming, but for understanding this in a very simple way, you can imagine respiration is constant, right? But photosynthesis has a seasonal cycle. Whenever photosynthesis is activity is high, CO2 in the atmosphere will go down, right? So when is it high? During summer time. So that's why summer is going down.
When southern hemisphere,
Yeah.
if we increase the tree
Yeah.
or something like that, if we increase,
Yeah.
is it affect in future CO2?
Well, southern hemisphere, where is the line?
It's whatever areas which tree cover is not there.
Yeah, okay. Of course, you can, if you do that, you can modulate that. You can modulate that. You can reduce that. But why would you do that? Right? What is the reason for doing it? This is, okay. Now, let us look at, some of the emission numbers and where that carbon is going. That is given rate of anthropogenic CO2 emission. So right now, this figure is shown for the last decade, average over the last decade. So if you look at that, human beings are pumping about 8.6 gigaton of carbon through fossil fuel emission each year. And 0.8. So, I would say roughly, let's assume, so if you add up these two numbers, it's 9.4. Today we are actually about 10. Even just this is about 10. Okay? So, we are dumping approximately about 10 gigaton of carbon each year into the atmosphere. Now, what is happening to that carbon dioxide once it's in the atmosphere? About 25% goes into the ocean, and another 25% goes into the land biosphere, and the remaining 45% actually stays in the atmosphere. That's a simple story, but it looks very simple to me today to learn. But how did we calculate this number? That's the Herculean task. It involves thousands of scientists to come up with this number. Just like any global budget, global radiation budget or global carbon budget, it's not some single investigator can magically arrive at these numbers. It involves painful work by thousands of scientists going and measuring around the globe, right? And then sharing the data, putting all of them together, and then finally arriving at a number. Now, since it involves so many people and so many years of observations, right? There's going to be error. That is why you can see these things have big error bars. In fact, look at the land. Here the error bar is 50% of the, not 50%, 20% of the mean actually. So the error in land sink. Anytime this number is passing, that means the land is taking up carbon. So that is called land sink, land carbon sink. So the error is pretty high. Look at this, this is ocean, sorry. So the ocean actually has 0.5, 20% error. You have uncertainty in the ocean value. And here it's worse, nearly 25%. Okay? Now, even the emissions have uncertainty. Look at the emission uncertainty, it's almost same as the number that we are predicting. Right? 0.5 and the value is 0.8. So the uncertainty is huge. Right? But at least fossil fuel, we have good handle on it. It's 8.6, but the uncertainty is only 0.4. So the deforestation has huge uncertainty. Land sink also has slightly bigger uncertainty. That I think you should be aware, because this is not coming from a single equation, so you can have a very good confidence in that. This involves, for example, how would you, even consider this deforestation? Estimating this is really too hard, because you really need to come up with an estimate of how much trees were cut in a year. But, it is really to, on a global scale, what is the amount of CO2 that is coming out because people are cutting trees. So there is a lot of assumptions that go into this kind of estimates. Okay, now here is our current emission. So for the last 25 years. So in fact, you can see that in last 7 years, 1990, our emission was only about 6 gigaton of carbon. Today, this is the estimate for 2013. We are 10. So we have increased the carbon emission actually by nearly 65% since 1990. 1990 was the time when Kyoto Protocol was signed, and the goal was actually to reduce carbon emission compared to 1990 level. But where we are, you look at this, this is 61% over 1990 levels, right? So I think the problem is really, the Kyoto has not obviously worked, because if Kyoto has worked, we should have had emissions below 6 gigaton today. But right now, the emission is 10 gigaton. This is just the fossil fuel emission. On top of that, there is also land emission, land from deforestation. Okay, I think let's go to very simple basics now for a couple of slides. So what is carbon? Carbon, the most important thing is it's essential to life. We are all made of carbon, right? Organic carbon. Okay, so the carbon atomic number is 6. It could exist in oxidized form or reduced form. And I'm sure you have to little bit think about your chemistry, very basic chemistry. What is oxidation? What is reduction? Anyway, so oxidation, carbon in the oxidized form is called inorganic carbon. Okay? And reduced carbon is basically called hydrocarbons. Right? It mixed with hydrogen. Right? And then the intermediate form is carbohydrate. I'll just give some examples as we go along. So carbon intermediate oxidation state, basically carbon glucose and etc. Their oxidation state is actually 0. Okay? So basically these two, intermediate form and the reduced form, they are combinedly called organic carbon. Okay? So here is some example and table. So this is the CO2 is an actually oxidized form of carbon, because its oxidation state is 4. Here, basically carbon has given its 4 electron outermost shell, right? It has 4 electrons. It has given it to oxygen. Okay? So because it has last electron, its oxidation state is +4, right? It has last 4 electrons. So this is a good example for inorganic carbon. So you have to basically calculate, if you really want to understand the oxidation state of, if you want to know whether you are dealing with inorganic carbon or organic carbon, you just calculate the oxidation state. Now, a good example for reduced carbon is methane. Here, methane is actually, carbon has pulled 4 electrons from the hydrogen. Okay, so here these are basically -4, and these are basically called hydrocarbons. If you look at, I'm sure, petroleum, for example, it's mainly hydrocarbon. Now, carbohydrates actually, because you can see there is an H2 and O also. Now, because of this, it has last 2 and it has also K2, so the net is 0. So basically, this is the building block for this particular molecule. Basically, it's the building block for carbohydrates. Okay, so it has intermediate there. Now, the first question is, on Earth, do we have more organic or inorganic carbon? Yeah? Inorganic. If it is inorganic, you tell me what form it is. Huh? Carbonates? CO2? Okay, so I heard two molecules now. And what is the other compound? Methane. Methane is organic, not inorganic. Okay, anyway, the question is, how many of you think carbon is mostly in inorganic form? Just raise your hand. I want to see whether it's majority or... Okay, quite a few. And the other way, organic form? Okay, there is a mixture here. Okay, let's say clear that. So it is actually inorganic form. Some of you got it. Okay, the largest reservoir is of course limestone, calcium carbonate. That's the kind of, I mean, I'm sure all of you know the white layered rocks. That's the calcium carbonate. And basically overlap is the form of limestone, right? But there is also another big inorganic carbon reservoir, which is basically bicarbonate in the ocean. This is also a huge number, but of course nothing cannot be still. This one is way bigger than what is in the ocean. But so organic carbon is actually very small. So we will see those numbers in the coming slides. Some schematics diagrams I have. So the first is, okay, let's look at simple chemical reactions. These are not prototypic reactions. There are multiple equations like this, but I'll just give you some simple examples to just illustrate the concept of carbon going from inorganic to organic form and organic to inorganic form. And both of them are actually put also as equilibrium reactions here, like two-way reactions. So you can see that primarily over land, the carbon interaction can be basically summarized in the form of photosynthesis and respiration. They are just opposite of each other. So, for example, plants, they use water that is taken up through the roots and CO2 in the atmosphere. In the presence of sunlight, they produce carbohydrate. And in the process, they release oxygen. Right? Now, I mean, of course, when, let's say, so this particular process is basically photosynthesis, and the reverse can also take place. For example, we breathe oxygen and use oxygen plus this is that food, carbohydrate, we digest it, which is actually called respiration process. And we basically produce that carbon dioxide as that, right? So, in fact, plants do both of them. For plants actually, for them to grow, as well as to maintain themselves, they actually perform the reverse reaction. So, it's very strangely, it is both ways it is happening at least, any instant. I mean, even right now, if you look at the plants outside, they are removing some CO2 and releasing O2 through this photosynthesis process. But at the same time, they are also doing the reverse reaction and releasing CO2. So it is, when you consider whether the land is taking up carbon dioxide or not, it really depends on the net between the two large processes. So that is where the real complication comes. If you have just photosynthesis, then the problem is simple. And whatever carbon that is taken up by the plant, you can easily calculate it, okay, it's removed from the atmosphere. But there is a competing process in the same plants. And similarly, plants, when they die, when that organic matter decomposes, the reverse reaction takes place. And animals, they consume this, they also perform this reverse reaction. So, what is happening is, in fact, if you consider more of an equilibrium state which existed in the pre-industrial time, actually neither carbon is going in nor carbon is coming out, because the net flux is zero. Okay? So that is where the real complication comes. So we need to calculate what is the net flux that is going into the land. Okay. Now I think that, okay, I have some secondary questions. When did photosynthesis actually begin on Earth? Any idea? Huh? 3.1. Okay, I think these are anyway rough numbers. So apparently photosynthesis began 1.5 billion after Earth was formed. And of course, it's all single cellular life. And then only about 1 million years back, we had multicellular life. And the really, the explosion of plants and the buildup of oxygen in the atmosphere took place about 600 million years back. Okay. All right. I think these are some interesting quantities for the global carbon cycle. First one is gross primary production, which means basically photosynthesis. You can calculate at the canopy level or small scale level. But what is the net amount of carbon that is taken up by a plant through photosynthesis each year? That particular quantity is a big number actually. It is close to, in fact, it is 120 gigaton of carbon. So each year from the atmosphere, plants are taking up 120 gigatons of carbon. It's a huge number. Remember, because if you look at the atmospheric CO2 content, it's 400 ppm, which if you translate to pentagram of carbon or gigaton of carbon, it is 800 gigaton of carbon. And out of the 800 gigaton of carbon, plants are actually taking up each year 120 gigaton of carbon. Then why atmospheric CO2 is not going down? They are releasing equal amount out of that. Through this process, autotrophic respiration and heterotrophic respiration, if you add them up, they are also equal to close to 120 petagram of carbon. So the net is really zero, very close to zero. Okay? So, autotrophic respiration basically refers to the carbon that is released in the oxidation process for growth and maintenance, okay, by the plants. And then, of course, this is a very widely used term, that is net primary productivity, because this is the amount actually plants are accumulating, the amount of carbon the plants are accumulating in them, because this is the photosynthetic intake and this is the amount they are releasing to maintain themselves and grow. So the actual growth, actual accumulation of carbon in the terrestrial ecosystem is the difference between those two. And then of course, this heterotrophic respiration refers to the oxidation, this decomposition that takes place in the soil. For example, the soil, you may have dead plants or plants that fell down because of a hurricane or something, and they eventually decompose, and they release carbon dioxide. So that particular thing is called heterotrophic respiration. So the net carbon uptake by the terrestrial ecosystem is really, you have to subtract this quantity also from this, because this is accumulation in the plant and this is the release in the soil. So since both plants as well as soil is considered as a single system, so you have to consider what is going in, what is going out. So when you subtract whatever going out, you get this particular quantity, that is net carbon uptake. So which is really a very tiny number compared to where we started with. Okay? Anybody volunteers to guess what to be this number compared to this? This is what literally matters to deal with climate change, because that is the amount that is taken up by the terrestrial system. Even though photosynthesis is so high, but there are so many last terms on the way. So how big it is? Any guess? I have shown you a couple of slides back.
26.
Huh?
26.
No. 26% was in relation to the emissions. So that number is about 2 gigaton, you remember, right? 2 gigaton. So 122. So it's a percentage or so. Okay, now let's look at what is happening in the ocean. In the ocean, carbon, actually what happens is, it first CO2 dissolves and forms what is called carbonic acid. Now, carbonic acid is a weak acid and it can dissociate, basically it can release its hydrogen ions. So you produce basically 2 types of carbonate ions, this carbonate and bicarbonate. Okay. Now, the sum of the dissolved CO2, carbonic acid, bicarbonate, and the carbonate ion. All of them have carbon, remember that. There is one carbon here, one carbon here, one carbon here, one carbon here, right? So these are all actually inorganic carbon, and they are all dissolved in the ocean. So this is called inorganic carbon. And this is how actually the reaction, I mean, again, look at all these reactions are equilibrium reaction, okay? And if you take a solution of carbon, I mean, seawater today, for the current pH value of 8 in the ocean waters, nearly 90% is 90% of the carbon is the form of bicarbonate, 8% in the form of carbonate, and very little in the dissolved form and carbonic acid. So this is what I talked about, the bicarbonate ion. It's an inorganic carbon which is in the ocean, okay? And it is produced when CO2 dissolves in the seawater. So this is a chemical. So I mean, if you look at the process, straight away you can see that I am explaining here a chemical process in the ocean. But for the land, I explained the biology, right? So the carbonate K in ocean is a chemical process, but in the land it is a biological process. Now let's look at, there is also interestingly another process which for our time scales probably do not matter, but for the history of that, it is a very important process which is called basically weathering and metamorphism. So carbon can be also removed from the atmosphere by another mechanism which is called weathering. So basically, this is the generic formula for a silicate rock. Now you can see this doesn't have carbon in it. So it basically can react with CO2 with a CO2 molecule to produce a calcium carbonate, silicate. So this is called silicate and this is called calcium carbonate. Okay. Now, basically, this is the simplest reaction I have written. So basically, I think the point is CO2 has been removed in this process from the atmosphere. This CO2 comes from the atmosphere. So this reaction basically tells you a removal process by geology, right? And this is also a chemical process. This is not a biological process. Okay? Now, this is basically called chemical weathering of rocks. There is also physical weathering because you can really, literally because of wind or rain, calcium carbonate, because calcium carbonate has a carbon in it. So it can be washed by the rivers to the ocean. I mean, that is called physical weathering. Okay? Alright, now, so this is silicate rocks. So this is basically, this rock is called silicate rock. And this one is, this particular component is the sedimentary rocks. Now, you may be wondering, by looking at this, I mean, if this is operating, we do have a lot of silicate rocks on there. Why carbon dioxide is not going down fast? Concentration in the atmosphere, why it is not going down? So this is where some quantitative sense is required. So I come to this question later on. Why, even though this is all the time happening, why this is not able to remove the atmospheric CO2 concentration? We are dumping 10 gigaton of carbon dioxide each year, but if this process is operating, it should have removed it. Okay, now, there are also, that was the simplest reaction. Now, it can also happen, these are other reactions for this weathering. What happens is, the sedimentary rock, this limestone, it can also, in the presence of water, take carbon dioxide molecule from the atmosphere to produce calcium and bicarbonate ions. Okay? And also, there is another way, this is another type of reaction with silicate. It pulls down, in this case, actually 2 carbon dioxide molecule. Okay, so there's a various reaction. But the essential point is rocks, particularly sedimentary rock or silicate rock, they can also remove atmospheric CO2 and produce this bicarbonate. Now, imagine what will happen is these guys will be washed by the rivers into the ocean, right? Now, this calcium ion and the carbonate CO3 in the ocean basically are used by certain marine organisms to produce the calcium carbonate in the shell and bone. Okay? Now, so it's all linked. Now, okay, here is the simplest picture of the carbon fluxes and stocks in the major reservoirs. Now, let's go one by one. This is a little old textbook. This is, I think some of you got this textbook, IISc 2007. Okay? Now, I think this figure is taken from there. So the atmosphere contains roughly, about 800 gigaton of carbon. Now, look at its reaction, interaction with land. If you look at the land, the vegetation biomass, it contains about 500 gigaton of carbon. So roughly, the similar amount as the atmospheric carbon. But soils on land, they have 1500 gigaton of carbon. So the soils actually contain more carbon in them than the living biomass actually. Okay? Now the flux, the interaction, you can see that 120 ppm. So this arrow refers to the photosynthesis, GtP, and this arrow refers to the respiration, total respiration, autotrophic plus heterotrophic respiration. So according to this figure, basic atmospheric CO2 content cannot be changed by the interaction between land and oceans, right? Because equal amount is going in and out. Similarly, ocean. If you look at this, ocean, what also happens is, I showed you this reaction in the ocean. Now, since these are all equilibrium reaction, the whole reaction also can proceed backward and CO2 can get out of the atmosphere also. Right? Just like CO2 getting dissolved, the bicarbonate basically can eventually release CO2. So these things are actually simultaneously going together. Just like over land, you have competing intake and outgassing. Similar process happens in the ocean also. CO2 is, in some regions of the world, CO2 is going into the ocean. In some other regions of the world, CO2 is actually coming out of the ocean as well. So, you see in this case, these are the conditions when, pre-industrial conditions, more of a pre-industrial. These numbers do not reflect what is happening today. So, 90 gigaton of carbon. Now, look at the ocean, the bicarbonate, which mainly contributes 38,000 gigaton. So, you can see how big it is compared to the atmospheric carbon. So, the oceans contain humongous amount of carbon in the form of bicarbonate. Okay? On the other hand, you look at the organic carbon in the ocean, it is very small. So in the ocean, so only about 600 gigaton of carbon is in the form of organic carbon. And the living carbon in the ocean is even tinier. The fishes and all the living stuff in the ocean is very small compared to living stuff here, 500 here and 1. Right? So, but anyway, the essential message is the oceans contain mostly carbon in the form of inorganic form. Okay? Now, if you look at these sedimentary rocks, mostly in the form of limestone. Limestone, of course, has some sediments still are preserved in the organic form. So that combination gives you more than a million. Yearly, 3 times, like this is, let's say, this is actually not 30 times or something, 30 times, yeah. So and fossil fuel is approximately about 5,000 gigaton. These are all just to give you an idea where the carbon is residing. And now look at the arrow here. So basically, when carbon is removed from the atmosphere, that is called the weathering reaction. Now look at the flux here. These fluxes are big, 120, 90, this is less than 0.1. That is why the rock weathering cannot remove atmospheric CO2. Because it is proceeding at a rate of less than 0.1 gigaton of carbon per year. On the other hand, we are dumping CO2 at the rate of 10. So where is 10 and where is 0.1? So they differ by 2 2 orders of magnitude. I mean, that is the reason why natural weathering cannot remove CO2 on a human time scale. Okay, here is a very elaborate diagram. I think it will take 30 minutes to explain this, but let us, I think I would suggest if any of you are interested, it is actually already available on the web. This is from the IISc latest report. If you go to chapter 6, I think, it's carbon cycle. This is a schematic diagram. I think I can quickly go through this. Atmosphere. 589, that is the amount of carbon that was there in the pre-industrial time. All these red numbers refer to whatever change that happened after pre-industrial time. So humans have increased the atmospheric load by 240 gigaton of carbon since pre-industrial time. And again, these arrows represent the fluxes. Now let's quickly have a look at these boxes here. As I said, this is the marine organic carbon, which is in the previous diagram shown as 1 gigaton of carbon. Here it shows as 3. And this is what is the carbon in the surface ocean. This is in the deep ocean. And this all organic carbon. In the previous diagram it was shown as 600 gigaton of carbon. Here it shows as 700. Right? And this is basically the amount of currently the ocean sediments. All these marine organisms, when they die, they deposit, right? Basically either organic or inorganic carbon settles down to the ocean. And the carbon content in that is about the same as the soil here, right? The soils also have about 1500 gigaton of carbon also. Now, other interesting thing is this figure, I think it has gone into detail of even how much the river budget is done. The carbon budget of the river. For example, you can see the rivers are taking, through the, 2 types of weathering. This is, I think, 0.3. Okay, anyway, this is 0.3. So there is 0.4 weathering, both physical as well as chemical weathering, getting into the rivers. And what happens is some of that. So the rivers are basically, rivers are outgassing some of that. And the roads, I can't really see that. 0.9. Export from, there is also from soils, there are streams that export that carbon. That is about 1.7. So the river input is 1.7 plus is 0.4. So 2.14 is actually getting into the rivers, and some of that is actually outgassed, as you can see here. 1 gigaton is outgassed out of 2.1, and then I think there is somewhere there is a river settlement. River settlement is about 0.2. 0.2 is settled down to the river floor, and then 0.9 basically reaches the ocean. So you have to close this carbon budget eventually. Okay. Anyway, this is another schematic diagram that basically came out very recently. This is essentially the carbon cycle, the fate of carbon I showed just a few slides back. Nearly 8.7 from fossil fuel, 0.8 from the deforestation also. So total is 9.4. Out of that, atmosphere retains about 4.3 gigaton. The land takes 2.6, ocean takes 2.6. Same, illustrated in a figure. Now, I think I already emphasized this. That is, the net land carbon flux is the key quantity one should be looking for. Because individual fluxes are big, like whatever I said, basically the gross primary productivity, for example, is 120, right? Now, the respiration could be 119. So it's a small difference that basically is the net removal of carbon dioxide from the atmosphere. Now, the problem is, so you are taking, it's a difference between 2 large numbers which have huge uncertainty. So, if the uncertainties are large, you could be getting even wrong sign for the net flux. For example, the ocean, whatever is going in is 92 gigaton of carbon. Whatever is coming out is 90. Now, suppose your error in one of them is 10%. Then it's very difficult to actually, you will lose the sign of, you will have uncertainty even in the sign whether the ocean is taking up or or releasing CO2. So I think this you have to keep in mind. Now the interesting question, this is a very fundamental concept. What is the lifetime of CO2 in the atmosphere? I'm sure some of you must have heard about it, that CO2 has a long lifetime in the atmosphere. That is why it is a serious problem. Climate change is a serious problem by CO2 because it has a long lifetime. Now, can anybody tell me what is the lifetime of CO2? 200 years. I can't hear someone, one person, what is your answer? 120 years.
60 to 120 years. 60 to 120.
130 years? Yeah. Now, how did you get that? What is that? I'm sure, this is where science is all about curiosity and thinking. Now, you all have got this number from somewhere. Did you ever think about it? How it is estimated? Now, I'm going to ask you relatedly, think about this. Now, I have elaborated the question here. The atmospheric content is right now CO2 quantity is 800 petagram of carbon. Land photosynthesis is, this is GPP, 120 petagram of carbon per year. And the solution in the ocean is 90. Now, if I combine this is close to 200. That means, it should be only 4 years, right? Because the removal is at the rate of 200 petagram of carbon per year, and the atmospheric content is only 800. Then, but you are saying, some of you said 100. So if I look at it, that means in 4 years, every CO2 molecule might have gone either to the ocean or to the land. So, according to, if I really think about molecule by molecule basis, there is a very good chance, 25% chance, or 1/4 of the CO2 molecules in the atmosphere will be either they will go to land or ocean in a year. So that means in 4 years, the atmospheric CO2 should have either gone to the ocean or to the land. So the actual atmospheric molecular lifetime is only 4 years from this simple calculation. Then why do we say CO2 has a longer lifetime like 200 years or 300 years or 100 years, 120 years? Have you ever thought about that this way? In fact, people are asking this question. What do you say CO2 is a serious problem, it's going to stay in the atmosphere for a long time, but this calculation shows me CO2, definitely any molecule of CO2 that is in the atmosphere would have gone into the land or ocean in 4 years' time.
So this will be net rate or what the rate?
That is GPP, that is not net. Okay, let's go to the answer here. Now, 300 years really refer to the time it will take for the carbon to get into the deep ocean. See, carbon will be going into the plants, but next year, suppose the carbon goes into a leaf. The leaf will fall after 3 months. The carbon is back into the atmosphere. So even though the carbon goes into either the ocean or land, it actually is back. So what is important is, in the previous question, in this question here, is 120 and 90. I should not be looking at that, the flux that's going in. I have to look at the flux that is net. So the net, if you really look at it, today's atmospheric CO2 is what, 800 gigaton. The net today, the rate which it is going inside in the previous schematic diagrams, you showed 2.5 and 2.5. So the net is how much? 5. So now you divide 800 by 5. Roughly you get 100 plus some years. So it is the net that matters. So what that means is the molecule that is in the atmosphere, even though in 4 years time it will go either to ocean or land, it's again quickly back up. So you really have to really calculate what is the amount of CO2 each year that is permanently removed from the surface ocean and kind of the fast food pools in the land. You have to really think about permanent removal of CO2 from the atmosphere. So for that you have to consider the net fluxes, and that gives you 800 divided by approximately 5. That's why you get the number on the order of hundreds of years. So you have to be careful about how you estimate your residence time or lifetime. Okay. So there used to be a very huge controversy about this in the last IISc, because how you deal with this. I think the simple physical understanding is the following. Like as I said, that we need to really think about what is the rate at which it is permanently removed from the atmosphere. That means how fast it is going into the deep ocean. Okay, so here is the picture of the long-term carbon cycle. So basically, carbon, if you really don't have our anthropogenic activities, right? So what will happen is the real natural carbon cycle is carbon basically CO2 comes out of the volcanic vents. And the rate is approximately about 0.1 gigaton of carbon. This is the long-term, real natural carbon cycle. Okay. Now, the way carbon is in this case removed is basically CO2 is basically pulled by the weathering reaction, and the weathering reactions basically bring calcium and bicarbonate ions in the ocean. And in the ocean, there is already carbonate ion. So the marine animals use the calcium ion that comes from the rivers, and they use the carbonate ions, and they form shells or whatever, right, bones. And when these organisms die, the calcium, basically the shells are made of calcium carbonate. Now this calcium carbonate settles down to the ocean floor. Eventually, by subtraction, they are taken to the interior of the air, where the reverse reaction, this is the weathering reaction, exactly opposite direction. Calcium carbonate plus silicate, they, under very high temperature and very high pressure, silicate drop, right, and carbon dioxide is made. So, this is a real cycle, natural cycle in the long-term cycle. Basically 10,000 years or billion-year scale. Okay, let's say skip this out in the interest of time. Now, I think I just wanted to a little bit talk about what is the, I'm sure many of you must have heard these 3 planets, Earth, Venus, and Mars. They all had similar composition to begin with when the planets formed. Now, of course, they have all evolved eventually differently. They have life on Earth, we have water in 3 forms here, right? And if you look at Venus, it has lost the water. It's at a very high temperature. The surface temperature is 700 Kelvin or so. But here we have 15 degrees Celsius. Right? And Mars is, of course, too cold, and so they all have evolved differently. Now, the chemical composition was also the same. So, what happened to the carbon? Of course, for carbon scientists, it's an important question to also look at. Now, if you look at carbon in the Earth, there is some carbon in the atmosphere, there is some carbon in land in the form of the organic carbon in the soil or the plants, ocean, and then there is a lot of carbon in the limestone also. That's the biggest reservoir. So what happened to the carbon in Venus? Where is it? Is it in, of course there is no water there, so there is no ocean to support. Is it in the limestone form or is it in the atmosphere? So how did it go? Why did it go there? Okay, so we'll just to quickly take a look at that. I'm sure in the last lecture, I remember seeing Professor JS talked about this runaway greenhouse effect in the in Venus. So Venus was closer to the sun. So to begin with, it had a slightly higher temperature, right? I mean, this is the phase diagram for water, right? So this is the line that separates. This is vapor and this is ice, this is liquid, okay? So this is the total point here. So to begin with, you start at this point, then, I mean, of course, this line basically represents the water vapor feedback or whatever, right? Now, on that, basically, as the water vapor increases, right, the temperature increases, water vapor content increases, which basically further leads to warming. So that's why this arrow basically towards the right points to the water vapor feedback. So eventually, you hit a point in this equilibrium, a point very near to the triple point. Okay. So as we reach a point here where water can exist in all its three forms: liquid, say, gas, and solid. But if you look at Mars, it started out here and it hit the equilibrium point somewhere where both vapor and it's too cold, right? So it could not, the water vapor feedback could not take it to the liquid phase. Okay, so on Mars, basically water vapor is either vapor form or it is in ice form. Okay. Now in Venus, basically what happened was they could never reach this point. So basically, water, all the ice directly. Water basically became vapor, and of course water vapor has a very strong greenhouse effect. So the planet warmed, became too hot, and then of course all the water vapor that goes all the way fills the atmosphere, the sunlight would break it, and basically all the hydrogen escaped into space, and the oxygen, which was heavier molecule, was basically used for oxidation. Okay, so the oxygen that was left out in this runaway process, that is used basically to oxidize most of the chemicals in Venus. Now let's look at a quick process here. So basically Venus was close to sun, and because of water vapor feedback, it ran into this runaway greenhouse effect. Now, once you do this, of course you have no water, because weathering actually requires water. So because you don't have water, the weathering of rocks basically stops. Now, so basically the degassing of CO2 from volcanoes, yeah?
Sir, I don't understand. What is that?
Oh, I thought that's what I was explaining. Runaway greenhouse effect is, I'm sure all of you heard about this positive feedbacks to water vapor, right? Have you? Feedback lecture, right?
Yes.
In the feedback lecture, basically if you, let's say, you increase the planet's temperature, you increase water vapor, right? And increase water vapor, it can lead to further trapping of radiation. Now, which can lead to further warming. Now, further warming leads to more water vapor, right? So you can go amplify. Now, unless there is another feedback to stop this, you could basically amplify this, and eventually the planet would become extremely warm, and you can fill the whole atmosphere. It's like a more runaway effect, nothing to stop. So that is what is supposed to have happened in Venus. So the entire water in Venus basically evaporated, and it all became vapor form. So all the water in Venus basically filled the atmosphere in the form of gas. If you leave it to the situation. If you don't have the situation, of course, you condense and form water and ice and things like that. But as the planet becomes hot and hot, you can't support liquid and you can't support ice as well. So the entire H2O became vapor in Venus. So that is what is called runaway greenhouse effect. Okay? So now in that situation, because you don't have water, right? Water is important for weathering reactions. So the weathering actually stops. So basically, all you have left is, in that cycle, if you look at this, if you go back to this, in this cycle, as you can see, the carbon dioxide concentration in the atmosphere is maintained by a balance of two things. One again, CO2 flux and removal of weathering. So they are balancing each other, right? Now, if you stop one process and only the other process is operating, then that process will win. So in Venus, what happened was, this weathering part basically stopped. But the CO2 keep on coming out. So basically what is happening is, CO2 in the atmosphere kept on accumulating. Right? So basically closing one part of the cycle. So you just need whatever is coming out from the volcanoes, that CO2 is accumulating in the atmosphere. That is why right now, if you look at any planetary atmospheric textbooks, you will, first thing you will learn is, Venus atmosphere has 95% or 98% CO2 atmosphere. Here, what is nitrogen? I mean, here nitrogen is filling up the atmosphere. There, in Venus, CO2 is filling out the atmosphere. Okay. So basically, carbon, all carbon in the planet Venus has accumulated in the atmosphere. So it's kind of different fate for carbon in that planet. Now Mars, what has happened is, Mars is far away from Sun. So apparently its interior cool fast. So the volcano basically, no volcanoes. So the geologically the planet became dead. Okay? So the silicate rock weathering basically, it bent. So all the carbon has actually ended up in the sedimentary rock. I mean, that's why if you look at, the graphic representation of Mars as a red planet, you would always see, layers of rock. So Mars is actually filled with, all the carbon in Mars basically ended up in the sedimentary rocks. Okay, now I think we got only a few more time. So now I think already I had talked about this. Can silicate weathering remove anthropogenic CO2 emissions? It cannot, because here is the answer for that. That is, our fossil fuel emission is right now at the rate of 10 gigaton of carbon, but the weathering rate is only 0.1. So that means every year of emission will require 100 years of weathering to remove that carbon. That means if you are talking about centennial climate change, if you let weathering alone to operate, it's going to take 10,000 years time to remove the CO2 that we are going to put out in the atmosphere. So basically it will take 10,000 years to remove a century of CO2 emission from human activities. Now let's look at CO2 in the past. This is a little bit related to, did anybody talk about glacial versus glacial, interglacial cycles? I'm sure paleoclimate must have heard about it. Okay, anyway, this is the, how CO2, I showed you CO2 from 1958 to 2010. Now, let us look at CO2 in the past 1 million years. So this is, the time scale here is thousands of years, so this is 800,000 years. So if you look at the CO2 concentration here, CO2 has naturally fluctuated between anywhere from 180 ppm to 280 ppm. So on the other hand, today we are here. So just on this account, if you look at it, if humans were not on this planet, CO2 would still be here. So I think this very clearly graphically illustrates a signal from humans. If you look at CO2 records, it's because of humans, we just went above the natural variability. The naturally CO2 was fluctuating only between 180 and 280 ppm. Because of us, we shot out here. And also, this is the CO2 value in the last 2,000 years. So you can see that for 1900 years, out of the last 2,000 years, CO2 was fairly constant. Only in the last 100 years, it just shot up. So, really, looking at a little bit longer time scales of a million years, you can really see the signature, I would call it a footprint of humans on this planet. If you measure the chemical composition of the atmosphere, you can see the arrival of the human civilization on this planet.
So how can we reduce this radiation?
Yeah, they are basically measured and taken from what we call as ice cores. So you might ask, why only 1 million years? I think it's basically the ice that is formed in Antarctica. So it basically traps the air during that time. So it's basically you have to drill the ice, that was formed maybe, let's say 100,000 years, and you bring it to surface and you measure the composition of that bubble trapped in that ice. So that gives you the 3 years CO2 values. Okay, I think there are some interesting things in this graph. Number one, you can see that there is a regular oscillation which has a period of about 100,000 years. Can you see that? Because if you look at count the number of peaks, there are 8. So over 800,000 years. So now, what could possibly cause this 100,000 year oscillation, and why CO2 actually is, in fact, if you look at the graph very carefully, this is the temperature graph. So whenever the temperature was higher, CO2 was higher. Whenever the temperature was lower, CO2 was lower. So there is a very nice kind of correlation between these time series, and also, okay, these periods are called interglacial periods, and these periods are called glacial periods. And apparently, the temperature difference in those sites, the sites where this ice core was taken, the temperature difference has been almost about 10 degrees between glacial and interglacial cycle. So obviously, if you calculate the CO2 effect for 100 ppm difference, you can't get 10 degrees Celsius. So obviously, these temperature variations of 10 degrees in Antarctica, they are not driven by CO2. Something else must have driven it. And I think I would suggest you to read the books that are given to you when you registered for this course, and you will find the answer to that. But I think I'll just go to some other question here. What causes the glacial and interglacial cycle? Well, that's exactly the question anyway, I think. So apparently, the solar time variations in the orbital perennial of that is supposed to have initiated this, and ice has been the feedback between ice sheets in the northern hemisphere and solar radiation is believed to have caused this, they have been the triggers, and CO2 is supposed to be only responding to that temperature change. It is not that CO2 caused that climate change. CO2 was only responding to that climate change. That's the current understanding. Okay. Now, well, I think we are out of time. Let's see where we should be heading. I think, okay, let's see a couple of important points here. I think we talked about this particular time series where there is a seasonal cycle, and this seasonal cycle was believed to be, in fact, this caused by the terrestrial plants in the northern hemisphere. Now, CO2 values have been, of course, measured in other places, so where the local influence is higher. Now, we look at, this is a global CO2 as represented by nominal loss observations. Now, this is a CO2 measurement taken in high latitude, where basically this is Alaska, and this is the CO2 value taken up in the Antarctic, basically South Pole. So I think the key message I want you to look at is here the CO2 actually fluctuates between the seasons by 6 to 7 ppm. Between the summer and winter, the fluctuation is about 6 to 7 ppm. On the other hand, if you go to Alaska, the fluctuation is actually about 15 ppm, because there you are measuring really the local seasonal cycle, where during the summer there is a blooming of vegetation. During the winter, there is no vegetation at all. So you see that signature, very strong fluctuation. On the other hand, if you go to the Antarctic South Pole, there is no fluctuation. Because there is no local influence of vegetation. It is all through the year, white. Ice sheet. Nothing else. So the CO2 doesn't fluctuate much. So I think the basic point is the seasonal cycle at each location could have a global contribution plus a local influence. Now, CO2, so that is the seasonal cycle part of the carbon dioxide concentration in the atmosphere. And CO2 in the atmosphere could also vary interannually, because that could be dictated by the sources and things. For example, let's say some years humans may be inputting 8 gigaton of carbon. I mean, there is no magic about every year we have to go at a fixed mathematical formula decided carbon dioxide emission increase. 1 year, for example, this year we will be emitting 10 gigaton of carbon. Next year, for some reason, let us say if there is an economic downturn, we could actually be emitting only, let's say, just as an exaggeration, we could be emitting only 6 gigaton of carbon. Then the carbon dioxide concentration in the atmosphere is not going to rise as you see this year, right? So there are a lot of factors that could be affecting the atmospheric CO2 concentration. So what is shown here is basically the annual increase in atmospheric CO2 concentration as a function of the Central Pacific SST. So apparently, whenever you have El Nino, there is a lot of carbon actually emitted by the land. Because what happens is, ENSO has global influence. And whenever you have a very big El Nino, typically what happens is the Indonesian region, which has a lot of vegetation, it actually experiences drought. So the El Nino years are associated with higher atmospheric CO2 concentration because drought is associated with decomposition of the plant material in the atmosphere. So anyway, the basic message is CO2 can fluctuate also. It can experience internal variability. Now, so here is what is the rate at which CO2 is actually growing in the atmosphere from one year to the other year. So you can see that in the 1960s, CO2 in the atmosphere was growing at the rate of about 0.85 ppm. So this is in ppm. But on the other hand, if you look at this bar here, right now we are growing at the rate of 2 ppm. And also, it can change. In some years, CO2 can be growing at the rate of 2.5 ppm, and some years it can be as low as 1.5 ppm. But in general, you can see that constantly the CO2, except this decade, it has been decade after decade, the growth rate of CO2 in the atmosphere is increasing, which is not a good sign, right? Because at this rate, for example, you can easily calculate. If you go at this rate, the next 10 years, CO2 increase will be another 20. So by 2025, they may be close to 425 ppm. 420 or whatever.
So then between 1992 to when the growth is before and the 1988.
Yes. No, I think that there could be multiple causes. I think that one of the main causes is basically the deforestation activity reduced dramatically. In fact, if you look at the deforestation fluxes, at some point of time in the past, it used to be as high as 2 gigaton of carbon. Right now, it has come down to 0.6 or something like that. Okay, so there are, I believe that's mainly caused by the. Okay, then here there are some message about we can also influence the atmospheric CO2 concentration. For example, there is a lot of story about, I'm not sure how many of you are really following the economy. For example, 2008, there was a huge crash in the global economy. So because of that, the fossil fuel consumption, because whenever there is a strong economic activity, we use a lot of energy, so a lot of coal is burned. Similarly, a lot of people buy cars, that means we use petroleum a lot, and we economic activity means more fossil fuel emission. That means the growth rate of atmospheric CO2 concentration also could be higher. So these are some years when these arrows represent the years when the economic activity actually took a dive. So those years, the fossil fuel emissions also went down, and it was actually reflected in the atmospheric CO2 growth rates. I think, I don't think I'll have time to consider this particular important topic, which is basically, how I think, even though I have shown the influence of atmospheric, influence of fossil fuel emissions and deforestation on, only mainly I have shown its influence on the atmospheric CO2. Now, I haven't really shown how that is going to change the way land is taking up carbon, or how weathering will proceed, or how oceans will respond to this climate change, as well as the increasing atmospheric CO2 concentration. It looks like that itself could be another lecture. So we will literally stop here. I think, I hope you got just a good glimpse of, where whatever carbon we are putting in the atmosphere is going. And, obviously it is going, currently 50% is going into the atmosphere, 25% is going into the land, 25% is going to the ocean. Now, the big question is, will ocean keep taking the same similar 25% in the future? Similarly, will land keep taking up this 25% in the future? Those are big questions, and it seems that's not going to be the case. In fact, the rate of uptake by the ocean is predicted by models to decline with time. As global warming proceeds, more and more carbon will stay in the atmosphere. That's the message that we get from the model. The reason is the ocean gets stratified. A stratified ocean cannot take the carbon deeper into the ocean. So the rate of uptake by ocean will slow down. And the other reason is the ocean biology chemistry. That is something I really wanted to talk about. What happens is the ocean, carbonate ion is taken by each CO2 molecule that goes in. Now, as the CO2 increases in the atmosphere, the carbonate concentration in the ocean will go down. So the uptake of CO2 by the ocean also into chemical process-wise also declines. So the short message is that oceans will not be doing the same job as they are doing today. And the land also, the carbon, as the planet warms, the soil actually starts to respire more. So the land, the fraction that is taken up by land also will decline with time. And I will just to show you one important figure that is, that is actually in the IPCC reports. I'm skipping all the process. I mean, this is an interesting figure. You can see that what happens in the oceans as, okay, where is that thing? Okay. You can see the three concentrations. This is the carbonate concentration, this black line. This is the dissolved CO2 or carbonic acid, and this is the bicarbonate. Now, as you can see, current pH is about 8. So most of the concentration is the form of bicarbonate. Now, as you put more and more carbonic acid, more dissolved CO2, so you are going to push in this way because they are putting more. So you can see that the carbonic ion is reduced. You can see that as you go in this way, the carbonic acid is increasing, but the carbonic ion is going to. So this is what is called ocean acidification. The pH is going down, and the ocean becomes more acidic, and more acidic ocean, as you can see, these equilibrium concentrations, the carbonic ion is going down. So the less carbonic ion you have, less the ocean's capacity is to assimilate CO2. So this is a important thing, this is a very well-known biogeochemistry problem. That is, as ocean pH increases, the carbonate ion concentration, equilibrium carbonate ion concentration goes down, and equilibrium dissolved CO2 and the carbonic acid goes up. So some of the marine animals will have difficulty because the carbonate concentration. Now, I think I just want to show one more thing. That is a result from IPCC, which includes actually some of the geological processes also. Here is, what is shown here is, as suppose we put all the fossil fuels right now. I mean, there are three scenarios considered here. Let's see, what is this blue line? Blue line shows that if you put 100 petagram of carbon, that is 10 years worth of emission, what will happen? It seems in 100 years time, the land will take nearly, you can see that, 60% of that carbon, right? And then other 20% is taken up by the ocean. So in 1,000-year time scale, 100 petagram of, that is 10 years worth of emission, still, even after 1,000 years, 20% will be remaining in the atmosphere. This is the scary thing. This is the thing that is telling you that CO2 problem is, it's not just simply CO2 going into the land or ocean. There are other processes, feedback processes that kick in that basically prevents CO2 from being taken up. So even after 1,000 years, you can see that 20% of 10-year worth of emission actually remains in that market. But okay, now let's look at the other cases. This is 1,000 petagram line is here, and then there is a 5,000 gigaton of carbon. That's a huge amount of emission. If you do that, you can see that even after 10,000 years, nearly 10% of the carbon dioxide still remains in the atmosphere in the case of 100 gigaton of carbon emission, and in the case of 5,000 large emission, still more than 20% actually remains in the atmosphere even after 10,000 years. So which means, by putting some carbon dioxide into the atmosphere, you are really committing to a long-term climate change, because once the system, and I'm not showing some of the pictures, the temperature pictures, if you look at it, it's even scary, because once you reach temperature level, very high temperature level, it's very hard to bring that temperature back to previous level. So this is why the carbon problem is a long-term problem if you think only nature is going to act. Because these models have included the very well-known three effects that I have shown you, that is the uptake, ocean biodiversity, and even some of the weathering is actually included in this process. So even after including all three well-known processes, 20% of the carbon dioxide emission will remain in the atmosphere even after 10,000 years. So I think I will stop here, and if you have any question, you can ask me later on. And of course, we have some assignments. I hope you will learn a little bit quantitative knowledge from those assignments. Okay? Okay, we'll stop here.